What if the universe is trying to destroy itself, not in the dramatic way, not in a sudden explosion or a violent collapse, not in any way that would be visible to you or me or any civilization alive today or for billions of years to come, but quietly, patiently, relentlessly. Right now, at this exact moment, every galaxy beyond our local neighborhood is moving away from us. Not because it was launched outward by some explosion, not because something is pushing it, but because the space between us and it is expanding, stretching, growing. And here is the part that changes everything. It is not slowing down, it is speeding up. The expansion of the universe is accelerating. The galaxies are not just moving apart, they are moving apart faster and faster with every passing second, every passing year, every passing billion years. Something is causing this acceleration, something that fills all of space, every cubic centimeter of the void between galaxies, every region of space-time that has ever existed, with an energy that pushes outward. That drives the expansion. That is, right now, working to pull apart everything that gravity has spent 13.8 billion years assembling. We call it dark energy, and it is not a theory. It is not a hypothesis waiting to be confirmed. It is a measured, observed, confirmed feature of the universe we live in. As real as the chair beneath you, as real as the air in your lungs, as real as the light from the sun. Something is tearing the universe apart, and we have almost no idea what it is. In 1998, two teams of astronomers made a discovery that they did not expect, did not want, and spent considerable time trying to explain away. They were measuring the expansion rate of the universe using Type 1a supernovae, exploding white dwarf stars that always detonate with approximately the same intrinsic brightness, making them reliable distance markers across cosmic scales. By measuring how bright these supernovae appeared from Earth, and comparing that to how fast they were moving away, their redshift, the teams could determine whether the expansion of the universe was slowing down, staying constant, or accelerating. Everyone expected deceleration. The universe had been expanding since the Big Bang. Gravity, the attractive force between all matter, was working to slow that expansion. The only question was whether gravity was strong enough to eventually reverse the expansion and collapse the universe in a big crunch, or weak enough that expansion would continue forever, but gradually slow. Acceleration was not on the table. Both teams, the Supernova Cosmology Project led by Saul Perlmutter at Berkeley, and the High-Z Supernova Search Team led by Brian Schmidt at Harvard and Adam Rees at Johns Hopkins, found the same answer. The distant supernovae were fainter than expected, not because they were intrinsically dimmer, but because they were further away than they should have been. The universe had expanded more than expected in the time the light from those supernovae had been traveling. The expansion was not decelerating, it was accelerating. Both teams checked their data. They checked it again. They looked for systematic errors, dust absorption, evolutionary effects in the supernovae, calibration errors. They found none that could explain the result. The universe was accelerating. Something was driving that acceleration. In 1998, the discovery was announced to the world. It was met with a mixture of astonishment, skepticism, and, from those who had been tracking certain theoretical inconsistencies in cosmology, a kind of reluctant recognition. Something had been known to be wrong with the standard picture for years. This was what was wrong. Perlmutter, Schmidt, and Rees were awarded the Nobel Prize in Physics in 2011. The citation read, "For the discovery of the accelerating expansion of the universe through observations of distant supernovae. The force driving that acceleration was named dark energy, and it immediately became the dominant component of the universe's energy budget. Approximately 68% of the total energy content of the universe. More than twice the contribution of dark matter. More than 13 times the contribution of all ordinary matter. Everything we have ever seen, every star, every galaxy, every atom, is 13% of the universe. Dark energy is 68%. We are the minority in a universe dominated by something we cannot see, cannot touch, and cannot explain. The simplest explanation for dark energy is also the oldest. In 1917, 2 years after publishing his general theory of relativity, Albert Einstein was troubled by a problem. His equations, applied to the universe as a whole, did not produce a static universe. They produced a dynamic one, either expanding or contracting, depending on the initial conditions. But at the time, the prevailing scientific view was that the universe was static, eternal, unchanging, the steady-state cosmos of traditional astronomy. Einstein added a term to his equations to produce a static solution. A constant, the cosmological constant, denoted by the Greek letter lambda, that represented a repulsive energy inherent to space itself. A constant energy density filling all of space-time, providing an outward pressure to counteract the inward pull of gravity. When Edwin Hubble discovered the expansion of the universe in 1929, Einstein abandoned the cosmological constant. The universe was not static, it was expanding. The cosmological constant was unnecessary. Einstein reportedly called it his greatest blunder. He was wrong to call it a blunder. The cosmological constant is back, not to produce a static universe, but because it appears to be the correct description of dark energy. In modern cosmology, the cosmological constant represents the energy density of the quantum vacuum, the energy inherent in empty space itself. Quantum field theory tells us that empty space is not truly empty. The quantum vacuum seethes with virtual particle-antiparticle pairs constantly popping into existence and annihilating. This activity gives the vacuum a non-zero energy density. The cosmological constant is the observational signature of that vacuum energy, and its measured value, determined from the supernova observations and from the cosmic microwave background, corresponds to an energy density of approximately 10 to the power of -29 grams per cubic centimeter. Extraordinarily small, far smaller than any ordinary energy density we encounter, but non-zero and uniform across all of space, and therefore summed over the entire vast volume of the observable universe, enormous in its total effect. This tiny energy density, present everywhere in the universe, provides the repulsive push that is driving the accelerating expansion. The cosmological constant, Einstein's greatest blunder, restored to the equations after 80 years, and now the dominant component of the universe's energy budget. To truly understand dark energy, you need to understand the full history of the universe's expansion, not just the current accelerating phase, but the entire 13.8 billion year story of how the universe grew from a hot, dense fireball to the vast, accelerating cosmos we inhabit today. The universe has not always been accelerating. In the earliest moments, in the first fractions of a second, the universe underwent inflation. an extraordinarily rapid exponential expansion driven by the energy of the inflaton field. We discussed this in our Big Bang video. Inflation ended when the inflaton field decayed, and the universe transitioned to a hot, dense, radiation-dominated fireball. For the first approximately 50,000 years after the Big Bang, the universe was dominated by radiation. Photons and relativistic particles, moving at or near the speed of light, were the dominant component. In a radiation-dominated universe, the expansion is relatively rapid, but it decelerates. Gravity, working on the energy density of radiation, slowly puts the brakes on. At approximately 50,000 years, the energy density of matter, both ordinary and dark, overtook the energy density of radiation. The universe transitioned from radiation domination to matter domination. In a matter-dominated universe, the expansion continues to decelerate. Gravity, the mutual attraction of all the matter in the universe, works relentlessly to slow the expansion. The universe is coasting, but braking. If dark energy did not exist, the deceleration would continue forever, and the universe would either coast to a near stop or eventually reverse and collapse. For approximately 9 billion years after the Big Bang, more than half of cosmic history, matter dominated. The universe expanded but decelerated. During this period, the density of dark energy was always present. It is a constant property of space, but matter was dense enough to dominate the dynamics. Then, approximately 5 billion years ago, roughly 1 billion years before Earth formed, something changed. The universe had expanded enough that the density of matter had thinned out sufficiently. Matter density falls as the universe expands. As the volume grows, the same amount of matter is spread over a larger space, reducing the density. Dark energy density, by contrast, does not fall. It is a property of space itself. As space expands, more space is created, and the total amount of dark energy grows in proportion. 5 billion years ago, the density of dark energy overtook the density of matter, and the expansion stopped decelerating. It began to accelerate. This transition, from deceleration to acceleration, is called the dark energy domination era. We are living in it now. The universe has been accelerating for approximately 5 billion years, and unless dark energy changes its character, unless quintessence or some other dynamic component alters the picture, it will continue to accelerate forever. The full history of the universe's expansion is a story in 3 acts: radiation domination, matter domination, dark energy domination. We are in the 3rd act, and the 3rd act has no ending we can prevent. If the cosmological constant is vacuum energy, if it is the energy of the quantum vacuum, then we should be able to calculate it. Quantum field theory gives us the tools to calculate vacuum energy. We know the quantum fields that fill space. We know their properties. We can calculate the zero-point energy of each field, the energy it has even in its lowest possible state. Add them all up, and you get the vacuum energy. The answer quantum field theory gives is approximately 10 to the power of 94 grams per cubic centimeter. The observed value is approximately 10 to the power of negative 29 grams per cubic centimeter. The discrepancy is 10 to the power of 123. 123 orders of magnitude. This is the worst prediction in the history of science. By an almost incomprehensible margin. It is not a small error. It is not a factor of 2 or 10 or 1,000. It is a factor of 1 followed by 123 zeros. If the vacuum energy were as large as quantum field theory predicts, the universe would have expanded so violently in its earliest moments that no structures could have formed. No galaxies, no stars, no planets, no chemistry, no life. The universe would be a diffuse, rapidly expanding gas of particles, thinning out to nothing almost immediately. Obviously, that did not happen. The universe we observe has structure. We are here to observe it. So something is wrong. Either quantum field theory's calculation of vacuum energy is wrong, missing some cancellation mechanism that reduces the result by 123 orders of magnitude. Or the relationship between vacuum energy and the cosmological constant is wrong. There is some unknown principle that neutralizes the vacuum energy's gravitational effect. Or the cosmological constant is not vacuum energy at all, and the entire framework is misconceived. We don't know which. The cosmological constant problem, the question of why the observed vacuum energy is so much smaller than quantum field theory predicts, is arguably the deepest unsolved problem in theoretical physics. It sits at the intersection of quantum mechanics and general relativity. It may require a complete theory of quantum gravity to resolve. Without an answer, we are in the extraordinary position of knowing that dark energy exists, knowing how much there is, knowing what it does, and having no reliable theoretical explanation for why it has the value it does. We measured something. We don't understand what we measured. The cosmological constant assumes that dark energy is fixed, constant, the same value everywhere in space and at every moment in time. But what if it isn't? What if dark energy is not a constant property of space itself, but a dynamic field, something that evolves over cosmic time, taking different values in different eras of the universe's history? This is the idea behind quintessence, a class of dark energy models in which dark energy is a scalar field, similar in some ways to the inflaton field that drove cosmic inflation in the first second of the universe. A quintessence field would have an energy density that changes over time. In the early universe, it might have been negligible, allowing gravity to dominate and structures to form. At some point in cosmic history, roughly 5 to 6 billion years ago, it would have become significant enough to overcome gravity and begin driving the accelerating expansion. The behavior of quintessence is characterized by a quantity called the equation of state parameter, denoted W. For the cosmological constant, W equals exactly -1. For quintessence, W can take different values, and crucially it can change over time. If W is greater than -1, if dark energy is slightly less repulsive than the cosmological constant, the expansion accelerates more slowly than the standard model predicts. If W is less than -1, if dark energy is more repulsive, the expansion accelerates more aggressively. This leads to the possibility we discussed in our Fate of the Universe video, the Big Rip, in which dark energy eventually overwhelms all other forces and tears apart everything in the universe, down to the level of individual atoms. Current observations from supernovae, from the CMB, from the large-scale distribution of galaxies, are consistent with W equals -1, the cosmological constant. But the measurements are not yet precise enough to rule out quintessence. The error bars are large enough that a slowly evolving dark energy could be hiding within them. The next generation of cosmological surveys, particularly the Euclid Space Telescope launched in 2023 and the Vera Rubin Observatory currently coming online, are specifically designed to measure W with unprecedented precision. to determine whether dark energy is truly constant or slowly changing. If Euclid or Rubin finds that W is not exactly -1, that dark energy is evolving, it would rule out the cosmological constant and demand a new theoretical framework. It would be one of the most significant discoveries in the history of cosmology. And it would deepen the mystery of dark energy rather than resolve it. Because a dynamic dark energy field requires its own explanation, its own theoretical justification, that we do not currently have. In April 2024, the Dark Energy Spectroscopic Instrument, DESI, released its first major results from a survey of approximately 6 million galaxies. DESI is an extraordinary instrument. Mounted on the 4-meter Male telescope at Kitt Peak National Observatory in Arizona, it uses 5,000 robotic fiber positioners to simultaneously collect spectra from 5,000 galaxies at once. It measures the redshifts of those galaxies, how fast they are moving away from us, with extraordinary precision. By mapping the three-dimensional distribution of galaxies across vast cosmic scales, DESI can measure the signature of baryon acoustic oscillations, the cosmic scale sound waves that were frozen into the distribution of matter in the early universe, and that serve as a standard ruler for measuring cosmic distances and expansion rates. The DESI first-year results covered the first year of a planned 5-year survey. They provided the most precise measurements yet of the expansion history of the universe across billions of years of cosmic time. And the results were intriguing. The DESI data showed hints, not a definitive detection, but hints that the equation of state of dark energy may not be exactly -1. The data showed a slight preference for a value of W that changes over time, consistent with a dark energy that was somewhat weaker in the past and somewhat stronger in the recent universe. The statistical significance was not high enough to claim a discovery. The hints could disappear with more data. Systematic errors could be responsible. But the hint was there. If confirmed by the full 5-year DESI survey and by the Euclid mission and the Rubin Observatory, it would be revolutionary. It would be the first evidence that dark energy is not the cosmological constant, that it is something dynamic, something that evolves, something that demands a new theoretical understanding. The full DESI results, expected over the coming years, are among the most anticipated data releases in cosmology. The universe may be telling us something new about the force tearing it apart, and we are listening. There is a crisis in cosmology. Not a crisis of confidence, the field is producing extraordinary results, but a genuine, unresolved tension between two different ways of measuring the same thing. A tension that has grown more severe with every new measurement. A tension that may be pointing toward new physics, possibly related to dark energy. It is called the Hubble tension. The Hubble constant, denoted h0, is the rate at which the universe is currently expanding. It tells us how fast a galaxy is moving away from us per unit of distance. It is one of the most fundamental numbers in cosmology. And we can measure it two ways. The first way is the early universe method. Using the cosmic microwave background, the ancient light released 380,000 years after the Big Bang, cosmologists can model the early universe in extraordinary detail and extrapolate forward to predict what the Hubble constant should be today. The Planck satellite's analysis of the CMB gives a Hubble constant of approximately 67.4 kilometers per second per megaparsec. The second way is the late universe method. Using observations of nearby galaxies, measuring distances through a chain of standard candles, from Cepheid variable stars to Type 1a supernovae, astronomers measure the expansion rate directly in the local universe. The most precise measurements from this method, led by Adam Rees, one of the discoverers of dark energy, give a Hubble constant of approximately 73 kilometers per second per megaparsec, 67.4 versus 73. The discrepancy is approximately 9%, and the statistical significance has grown to approximately 5 sigma, the threshold that physicists traditionally use to claim a discovery. 5 sigma means there is less than a 1 in 3 million chance the discrepancy is due to random chance. Something is wrong. Either the early universe measurements are wrong, or the late universe measurements are wrong, or, most intriguingly, neither is wrong, and the universe is genuinely different in its early and late phases in a way that current cosmological models do not capture. The most exciting possibility is that the Hubble tension is pointing toward new physics. Perhaps dark energy is not the cosmological constant. Perhaps it was stronger in the early universe than the standard model assumes, what some theorists call early dark energy. A period of enhanced dark energy in the early universe could alter the sound horizon, the cosmic scale standard ruler used in CMB analysis, and reconcile the two measurements. Several early dark energy models have been proposed. They have had partial success, but have not convincingly solved the tension while remaining consistent with all other cosmological observations. Perhaps there is a component of dark radiation, additional relativistic particles beyond the standard model, that was present in the early universe and affected its expansion. Perhaps there is something subtler, a modification of gravity, a non-standard recombination history, a systematic error in the Cepheid distance ladder. The Hubble tension is unresolved. Every new measurement seems to confirm it rather than dissolve it. The discrepancy is real and growing, and it may be the crack through which new physics beyond the standard cosmological model, beyond the cosmological constant, beyond everything we currently understand about dark energy, is beginning to leak. Dark energy is not just an academic puzzle, it is determining the fate of everything. We explored this in detail in our video on the fate of the universe. But in the context of dark energy, the consequences deserve a deeper look. The accelerating expansion driven by dark energy means that the universe has a horizon, a distance beyond which objects are receding from us faster than light can travel from them to us. That horizon, the cosmic event horizon, is currently approximately 16 billion light-years away. Any galaxy beyond 16 billion light-years is already beyond our reach. Light from those galaxies is losing ground. It can never reach us because the space between us and those galaxies is expanding faster than the light can cross it. And the horizon is shrinking. Not in absolute terms, the universe is expanding, and the total volume of space is growing. But the region of the universe that can ever influence us, or that we can ever influence, is shrinking. Every year, more galaxies cross the horizon. Every year, more of the universe becomes permanently inaccessible. In approximately 150 billion years, roughly 10 times the current age of the universe, every galaxy beyond our local group will have crossed the horizon. The night sky will be dark. The vast richness of the galaxy-filled cosmos that we see today will be invisible, not because those galaxies have disappeared, but because no light from them can ever reach us again. And in the very deep future, hundreds of trillions of years from now, the last stars will burn out. The universe will enter the dark era. Everything gravity assembled, every galaxy, every star, every planet, will slowly be dismantled by the relentless outward push of dark energy as the expansion continues and accelerates. If dark energy is the cosmological constant, the expansion continues forever. Heat death, the slow, patient running down of everything, is the end. If dark energy is quintessence with W less than -1, if it grows stronger over time, the Big Rip is the end. In approximately 20 to 30 billion years from now, the expansion becomes so violent that dark energy tears apart galaxies, then solar systems, then planets, then atoms, then subatomic particles. Everything, simultaneously, in one final violent expansion of space beyond all limit. Either way, the universe ends. Dark energy is the mechanism of that ending, and it is already underway. We established that quantum field theory predicts a vacuum energy 10 to the power of 123 times larger than what we observe. This discrepancy, the cosmological constant problem, is not just a numerical embarrassment. It points to something profound about the nature of reality. For the observed cosmological constant to be so much smaller than the theoretical prediction, something must be cancelling the enormous quantum vacuum energy almost perfectly. Something must be reducing it by a factor of 1 followed by 123 zeros. Not exactly 0. That would be easier to explain, perhaps by some symmetry that makes the vacuum energy vanish completely. But almost 0. Incredibly, extraordinarily, almost supernaturally close to 0. But not quite. The precision required for this near cancellation is itself extraordinary. The cosmological constant has to be tuned to 123 decimal places to get the value we observe. This is fine-tuning on a scale that dwarfs anything else in physics. Why is the cosmological constant so small? One answer is the anthropic principle. We discussed this in our multiverse video. If there are many universes, an inflationary multiverse, with different values of the cosmological constant, then we necessarily live in one with a value small enough to permit structure formation. In universes with a larger cosmological constant, the expansion is too violent for galaxies to form. No galaxies means no stars means no planets means no observers. We observe a small cosmological constant, because only in universes with a small cosmological constant are there observers to do the observing. In 1987, 11 years before the accelerating expansion was discovered, physicist Steven Weinberg used this anthropic argument to predict that the cosmological constant should be small enough to permit galaxy formation, but not much smaller. He predicted a value within roughly 2 orders of magnitude of what was subsequently observed. This was a genuine, falsifiable prediction made before the measurement, and it was approximately correct. For many physicists, Weinberg's successful anthropic prediction is the most compelling evidence that the multiverse is real, that the cosmological constant takes different values in different universes, that we live in one of the rare universes where the value permits our existence. For others, the anthropic principle is a deeply unsatisfying explanation. It explains our observation by assuming an infinite number of unobservable universes. It tells us why we observe what we observe, but only by positing an infinite ensemble that can never be directly verified. The cosmological constant problem, and the anthropic answer to it sits at the frontier of physics and philosophy, at the place where our best tools of scientific reasoning begin to strain under the weight of the questions they are asked to answer. Just as some physicists have proposed modified gravity as an alternative to dark matter, others have proposed that the accelerating expansion might not require dark energy at all. Perhaps gravity itself behaves differently on the largest cosmic scales than Einstein's general relativity predicts. Perhaps the equations of general relativity, so extraordinarily well tested on the scale of the solar system, and even of binary pulsars, need modification when applied to the universe as a whole, across distances of billions of light-years. Several modified gravity theories have been proposed as alternatives to dark energy. The most studied class is called FR gravity, a modification of general relativity in which the Einstein-Hilbert action that generates Einstein's equations is replaced by a more general function of the Ricci scalar, the quantity that measures space-time curvature. In certain F of R models, the modification to gravity produces an accelerating expansion without any additional energy component. The geometry of spacetime itself drives the acceleration rather than an energy density filling space. Other approaches include scalar tensor theories, in which an additional scalar field is coupled to gravity, and massive gravity theories, in which the graviton, the hypothetical carrier of gravity, has a small but non-zero mass. None of these modified gravity theories has been confirmed. All of them face significant observational constraints. The most powerful constraint comes from the neutron-star merger GW170817, the event we discussed in our neutron-star video. That merger produced both gravitational waves and light, gamma rays, that arrived at Earth within 1.7 seconds of each other, after traveling 130 million light-years. This observation constrained the speed of gravitational waves to be equal to the speed of light to within 1 part in 10 to the power of 15. Many modified gravity theories predict that gravitational waves travel at a different speed from light. Those theories were ruled out by GW170817 in a single observation. The surviving modified gravity theories are increasingly constrained. They may not be ruled out, but they are under significant pressure. Dark energy, however mysterious, remains the simplest and most observationally consistent explanation for the accelerating expansion. Understanding dark energy is one of the central goals of observational cosmology in the 21st century, and the tools being deployed are extraordinary. The Euclid Space Telescope, launched by the European Space Agency in July 2023, is designed specifically to map the dark universe. Over its 6-year mission, Euclid will map the shapes of approximately 1.5 billion galaxies and measure the redshifts of tens of millions more, covering approximately 1/3 of the entire sky. By measuring the shapes of galaxies, distorted by gravitational lensing from the dark matter and dark energy between us and them, Euclid will produce the most precise map yet of the dark matter distribution across cosmic time. And by measuring the positions and redshifts of galaxies, it will track the expansion history of the universe with extraordinary precision, pinning down the equation of state of dark energy to within 1%. The Vera Rubin Observatory, the legacy survey of space and time, beginning full operations at the Cerro Pachón mountain in Chile, will photograph the entire southern sky every few nights for 10 years. In doing so, it will discover an estimated 10 million Type 1a supernovae. the same type of exploding stars that led to the discovery of dark energy in 1998, providing a vastly larger and more precise dataset for measuring the expansion history. Together with DESI, now in the middle of its 5-year survey, these instruments represent the most powerful assault on the mystery of dark energy ever mounted. They are not guaranteed to solve the problem. Dark energy may prove to be the cosmological constant, real, dominant, and theoretically inexplicable, and no amount of precision measurement can explain why the cosmological constant has the value it does. But they will constrain the possibilities with unprecedented precision. They will tell us whether dark energy is constant or evolving. They will test modified gravity theories against observation. They will map the history of the accelerating expansion in detail. And perhaps, in the data from these extraordinary instruments, there will be a hint, a deviation from the cosmological constant, a sign that dark energy is something more specific, something with a physical explanation, something that points toward a new understanding of the universe. We are listening more carefully than ever. Dark energy is 68% of the universe. Sit with that for a moment. Not 68% of some exotic corner of reality. 68% of everything. Of the total energy content of the observable universe. More than 2/3 of all that exists is something we discovered 26 years ago, cannot directly detect, cannot reproduce in a laboratory, and cannot theoretically explain. This is not a gap in our knowledge that will be filled by the next experiment or the next paper. It is a fundamental, gaping, embarrassing hole in our understanding of the universe we live in. The physics we have built over 4 centuries, from Newton to Einstein to quantum mechanics to the Standard Model, describes approximately 5% of the universe. The ordinary matter that we are made of, that we can see and touch and measure. The other 95%, dark matter and dark energy, are unknown. We have mapped the unknown. We have measured it. We have characterized its behavior. We know where it is, how much there is, what it does to the geometry of space-time and the expansion of the universe. But we do not know what it is. We are, in the most literal sense, ignorant of the majority of reality. And dark energy, the dominant component, the force driving the fate of everything, is the deepest mystery of all. It fills all of space. It has been present since at least the epoch when its effects became measurable, several billion years ago. It may have been present since the Big Bang. It is present here, in this room, in every cubic centimeter of space around you. You are immersed in dark energy. Right now. As you watch this video, you cannot feel it. No instrument has ever directly detected it. It interacts with ordinary matter only through gravity, and its gravitational effect on small scales is so tiny as to be completely unmeasurable by any instrument we can build. We know it is there only because of its effect on the universe as a whole, on the expansion, on the geometry, on the fate of everything. The universe is telling us something important, something about the nature of space and energy and the vacuum, something that our current theories, for all their extraordinary success, are not equipped to hear. Dark energy is the universe speaking in a language we have not yet learned. What if the universe is trying to destroy itself? We asked that question at the beginning. And now, having followed the physics as far as it goes, we can give a more precise answer. The universe is not trying to do anything. The universe has no intentions, no goals, no preferences. But something in the fabric of space, something in the energy of the vacuum, or in a dynamic field pervading all of reality, or in some deeper structure of space-time that we have not yet understood, is pushing everything apart, quietly, patiently, relentlessly. It has been doing so for at least 5 or 6 billion years, since before our sun was born, since before Earth existed, since before the first complex life appeared in the oceans of a young planet orbiting an ordinary star in the outer arm of an ordinary galaxy. And it will continue for as long as the universe exists, pushing galaxies beyond the horizon, emptying the sky, dismantling everything that gravity assembled. We measured it, we confirmed it, we gave it a name, and we looked at it and said, honestly, we don't know what you are. That honesty, that willingness to measure something, confirm it, name it, and admit ignorance about its nature, is perhaps the most important thing science has ever demonstrated about itself. Not the equations, not the predictions, not the Nobel Prizes, the honesty, the willingness to say 68% of everything is something we don't understand, and we are going to keep looking until we do. Euclid is watching, Rubin is watching, Deci is watching, a generation of cosmologists is watching, and somewhere in the data they are collecting, in the light from billions of galaxies, in the baryon acoustic oscillations frozen into the fabric of space, in the shapes of galaxies distorted by the invisible universe, the answer may be waiting. Dark energy is real. It is here. It is tearing the universe apart, and we are going to understand it.